Hello everybody, I am PROTIK Pal. In this talk, we'll be discussing about how to prove any NP statement jointly, distributed prover zero knowledge protocols, in short DPZK. Here we'll start with the definition of zero knowledge protocols. Here we have a prover and a verifier. The input to the prover is a statement X and a corresponding witness W. The input to the verifier is the statement X. The prover claims that the statement X is true. That means there exists a deterministic algorithm M which takes X and W as input and outputs 1 if it is true. The task for the prover is to convince the verifier that the statement is indeed true without revealing any information about W. For that, the prover and the verifier can have interactions. A zero-knowledge protocol must have the following three properties. First is called completeness. If prover and the verifier are both honest, then verifier will always accept the proof. Second is soundness. That is, if the prover is cheating, that means either the statement is false or the prover does not have a correct witness, then verifier will reject the proof almost surely. And third is zero knowledge. That says at the end of the protocol, the verifier learns that the statement is true but nothing else. Now we will discuss the distributed witness setting. Here, instead of one prover, we have a group of provers. Together they claim that the statement X is true. Corresponding to the statement X, there exists a global witness W. However, none of the provers have the witness W. Instead, they have a private share of the witness W. Putting all the shares together, one can obtain the global witness W, which yields X is true. A distributed prover zero knowledge protocol needs to satisfy the following two conditions. One is privacy, that says no prover learns any other prover's private information, and second is zero knowledge. It says verifier should learn nothing about prover's secret. Ideally, all provers may send their shares of the witness to a trusted third party, which can execute a standard zero knowledge protocol with the verifier on behalf of the prover. However, in real life, we may not have such a trusted third party. The primitive DPZK has various applications. One of the applications is multi-wallet anonymous payments. In the era of digital currency, it is required to facilitate users with multi-wallet transactions where multiple users can execute a single transaction. However, to validate the transaction, the users need to ensure certain conditions are met without revealing their private information to maintain the anonymity. In such scenarios, DPZK can be used. For example, consider a cryptocurrency where P1 has coin C1 and P2 has coin C2. Together they claim that their coins are unspent and the combined value of their coins are more than a publicly known value V. Similar to this, another use case is auction with joint bidding using cryptocurrency, where parties opt for joint bidding so that they can have a higher chance to win the bid. Another application is publicly auditable MPC or multi-party computation. MPC is a tool that allows multiple parties to privately evaluate functions on their private inputs. For a standard MPC, if all the computational parties are corrupt, then neither privacy nor correctness is guaranteed. But publicly auditable MPC ensures correctness even if all the parties are corrupt. We can achieve this using DPZK, where all the computational parties jointly prove that they did the computation correctly. In this work, our contributions are mainly in threefold. First is we are giving a formal definition of distributed proof of zero knowledge systems. Second, we build a compiler that takes any IOP based zero knowledge proof system and gives another zero knowledge proof system which supports distributed proof generation. An IOP based zero knowledge protocol means that the prover constructs an oracle and gives the oracle access to the verifier, where the verifier makes polynomially many queries to the oracle and convinces itself that the statement is true. And finally, we give a new protocol graphene which is efficient in single prover as well as in the distributed prover setting. While giving the definition of DPZK, we observed that the efficiency measures of standard zero knowledge is not adequate to judge the efficiency of a distributed prover zero knowledge protocol. For a standard zero knowledge, a prover's efficiency is measured by the proof size and the proof generation time, and a verifier's efficiency is measured by the verification time. In the DPZK, along with these parameters, we also need to consider the number of interactions among the provers and the amount of communication among the provers to generate the proof to judge the efficiency of the protocol. Now we will briefly discuss the idea of our compiler. It takes any IOP based protocol. Consider Pi to be an IOP based zero knowledge proof system. The prover computes the oracle and the verifier makes polynomially many queries to the oracle. Then the verifier receives the data from the oracle corresponding to the queried location. Using this, it convinces itself that the statement is true. To support distributed proof generation, our compiler uses homomorphic commitment scheme. In the compiled protocol, the prover computes the oracle and the commitment of it and sets the committed oracle as the final oracle. The verifier makes the same queries to which it receives committed data from the oracle and corresponding opening from the prover. The binding property of the commitment scheme ensures that the prover cannot send any wrong value after the oracle is set. The verifier checks if the openings are valid or not, followed by the same verification as in Pi. For the distributed prover case, prover starts with their shares of the witness and execute an MPC to obtain a sharing of the oracle. Now locally, they compute the commitment of the oracle and send the committed value to a designated aggregator. The aggregator, using the homomorphic property of the commitment scheme, combines the oracles and computes the final oracle, which is given to the verifier. The verifier makes its queries, which is forwarded to the provers. Then the prover sends the corresponding opening to the aggregator, which is combined and sent to the verifier. Note that the hiding property of the commitment scheme ensures that the aggregator cannot learn anything more than what a verifier can learn. Also, the binding property prevents any prover from deviating from the committed values. Finally, the verification is the same as in the single prover dpi. Using our compiler, we compiled few state-of-the-art popular zero-knowledge protocols such as Ligero, Ligero++, Aurora, and Bulletproofs. Here we can see that our compiler preserves the proof size of the protocols. However, we can see in the proof generation time and verification time, there is some additional overhead. This is due to the computational cost of the commitment scheme and the verification of its opening. We also observe that protocols with fewer number of oracles perform better in the distributed prover setting. Since for each oracle, it may require additional interaction among the provers to generate the sharing of the oracle. Thus, Ligero, Bulletproofs, and Graphene has better communication among the prover as well as number of interaction among the provers in comparison to Ligero++ and Aurora. Finally, we can see that our construction Graphene has better communication among the prover in comparison to any of the other protocols. To understand the performance of Graphene, we provide a comparison with Ligero and Bulletproofs. We observe that Graphene has better proof size in comparison to Ligero. For proof generation time, Graphene and Bulletproofs have a comparable proof generation time. And for the case of verification time, it outperforms both Ligero and bulletproofs in terms of verification time. Finally, in the distributed prover setting, we considered a ZCash network where two parties P1 and P2 having coins C1 and C2. Together they claim that the coins are unspent and the combined value of the coin is more than a publicly known value V. In the ZCash network, this claim can be verified by a circuit which is of size 4 into 10 power 6. We see that the communication for bulletproof is 2 times more than the communication of graphene. For proof generation time, the bulletproof performs 2 times better than graphene. However, this is compensated in verification time where graphene performs 25 times better than bulletproof. Here I'll end the talk by restating the contributions of this work. Here we give the notion of DPZK. We construct a compiler which takes any IOP based proof system and gives a distributed prover zero knowledge protocol. Finally, we build a new protocol graphene which has better proof size, better proof generation time and better verification time, and also it has good communication among the provers. Thank you.